rather like a mirror image of what we had yesterday morning, because now we're going to be talking about studies that stop for futility, and that, remember, is where the early results in the data seem to show that nothing much is going on, that the treatment effect is very small or zero. So we're going to look at the implications of that. Is that too loud, or can you adjust? Is it okay? Not too loud? It's okay. All right. Right. So here's the outline for today. So we've only got 3 topics, so hopefully we'll get through it a little bit faster than the session yesterday morning. And if things go well, what I would like to do is take at least one of the papers that we're going to review and discuss that before the coffee break. Okay? That's a hope. If it doesn't work, no problem, we'll just do it after the coffee break, but I'd like to try and do at least one of those this morning at some point. Okay? So the first topic then this morning is going to be, we're going to look at the impact of stopping for futility again on the estimated treatment effect to see what that does. And we'll reverse the order of yesterday because it's a mirror image, right? So first of all, we'll have a little look at the theory, and then we'll look at some of the empirical evidence in the literature about what happened in studies that did actually stop like that. Okay, so just to remind you, this is schematic showing you what might happen to a clinical trial over time as it accumulates the data. And assuming you have no bias, which is a big assumption sometimes, but assuming you have no bias, eventually you'll converge to the true effect, which here I've just shown somewhat arbitrarily would be for benefit. Okay. However, along the way, you may see this we call the sort of random high, and you cross a threshold indicating that the early data are suggesting a strong effect, and so you decide to stop for benefit. And of course, you can also stop on the other side. This particular study here in the early data is showing an effect in the opposite direction. So if you had a criterion or a stopping rule for that, which you probably should have, then you might decide to stop for harm there. So that's just the same problem as we had yesterday, just with a change of sign. You set up the threshold in the same sort of way and control the type 1 error. This study seems fortunately to behave quite nicely and seems to be quite close to the true effect all the way along the way. So if you had happened to stop for some reason at an early point on that study, the middle study, you'd actually get close to the right answer. But that would not happen because of one of the stopping rules, right? Because you haven't crossed a threshold here. It would just be for some other reason. So for example, if you're doing a pharmacology study and the company decided to stop making the drug that you're using, you'd have to stop the study. And you do the analysis, and by luck it would turn out that you had the right answer, but of course you wouldn't know that. It would be a very uncertain estimate that you would have. Now, in this case, in the study that goes down here, it initially shows a period when you might stop for harm, but let's suppose that didn't happen. Let's suppose it wasn't sufficiently extreme, and it carries on, and at this point you've got a fair amount of data. And you might have a look at this and say, well, the data are very close to no effect. So that would be a situation, if you did an interim analysis there, you might decide to stop for futility, that it's disappointing, it's nowhere near close to what you had planned. If this was the planned delta, it's actually going slightly in the opposite direction. So that would be the question you would face at the point of the interim analysis. Should we do a stop for futility? Okay, so we get the general idea here. I think this is more or less the same as we had on a slide yesterday. Generally, the idea of having an interim analysis or an early stopping rule or a guideline is to reduce your expected sample size. So you have fewer patients involved in the study, which is good for everybody, of course. And you can get the study done faster, so you can either hopefully identify a superior treatment on the basis of benefit, or in this case, this is what we're talking about this morning, you would identify more quickly the lack of a treatment effect, and that's what we call futility. Okay, so you do that quickly, and then stop. And of course all of this is good from the point of view of budget and energy and all of those other things that we talked about. If you stop sooner, you're not wasting as much time on something that doesn't seem to work. Okay, and again, I think this is again quite similar to a slide we had yesterday, that most of the literature in this area actually talks about inferential properties, and that is primarily concerned with type 1 error rates and trying to avoid having false positive results too often. Remember Dr. Iyer yesterday, I don't know how many times he said, what's the problem here? It's alpha, right? It's type 1 errors. So that's mainly where the literature has gone with this, and quite rightly so, because we want to avoid false positive findings if possible. So we can do that by controlling type 1 error rates at the interim analyses, and Dr. Iyer yesterday gave you a whole bunch of methods where you can adapt the study in various ways and still control the type 1 error. So that's all to the good. But alongside that, there's this question of estimation. We still want to get an estimate of the treatment effect outside once we've done the study. And the question then is, how does having this stopping rule actually affect your estimate of the treatment effect? So that's mainly what I'm going to talk about now, the issue of estimation in studies that stop for futility. And we'll look both, as I said, at the theory and then also at some of the literature, again looking at actual studies that did stop now for this particular reason of futility. So, this is sort of the theoretical agenda at the moment then. We're going to look at how, if you stop for early for futility, and this would be a limited treatment effect or no treatment effect, what does that actually tell you? And the usual procedure in a case like this is to calculate what's known as conditional power. And I'll explain what I mean by that in a moment. But basically, very briefly, conditional power is asking, do we still have enough power for the remainder of the study if it carries on? If it was to carry on and we could complete the total sample size, what do we think our conditional power would be? And I know I said some things yesterday or the day before actually, that you shouldn't compute power based on the observed rates, okay? But this is slightly different because now we're talking about effectively the power of not exactly a new study, but the power if we get additional data in this same study. So I think that is a very legitimate question. And we have in fact seen that that's a very common method that's used in studies that seem to be showing little effect. So the idea is you work out the power at the point where you have the early data, and that's what's called conditional power. And if that value of conditional power is low enough, you think that the study then is unlikely to show an important effect if you go to the full sample. That's the conclusion, right? So let's say you compute the power, conditional power, and you find it's only 10%. So that means that you only have a 10% chance of showing a significant result, even if you go to the full sample size and complete the study. So on that basis, you might decide to stop the study. Okay? On the other hand, even if the results early on are quite disappointing with a limited effect, you compute the conditional power. Let's say the conditional power is now 80 or 90% still. Well, then you would say, it's not going so well, but I've still got a reasonable chance, I've still got reasonable conditional power to achieve a significant result if I complete the study. So in that case, you'd probably continue. That would be your decision. Okay, now the issue of estimation is again a mirror image of what we talked about yesterday. If you stop the study early, because it seems to be showing, I'm just going to go back if I can to this diagram. You remember when we talked about stopping for benefit, it's because you've gone over a stopping boundary in the direction of benefit, and because you deliberately stopped at that selected point, you have what we call the random high. So you're going to overestimate the treatment benefit. Remember that? And that was the concern there, that if you stop for benefit, It's going to look good, but it's probably going to be an overestimate of the truth. Now, in this case, if we do an interim analysis here, where we're stopping because it's a very small or even a slightly negative effect, the counter image of that is we'll have a random low, right? So on average, in the studies that we stop for futility because they're showing disappointing results, on average, we will underestimate the effect. So that's the risk that we take, right? So here's the truth on this line here, and we do the interim analysis, and if we decide to stop because it's so disappointing, we will actually have underestimated the effect. So that's the random low as opposed to the random high. So going back to where I was before, that's what it says. We expect studies that stop early for futility to underestimate the amount of benefit or the treatment effect. And once again, there's another mirror image here. If we do this interim analysis and we look at the possibility of futility but decide not to stop, we keep going, well, because we overestimate in the studies that do stop, there's a balancing effect in the other direction that we will underestimate the benefit for those. So if you do this interim analysis for futility and you keep going to the final target size, you actually would slightly underestimate the benefit in that study. Okay, it has to balance out, right? Because it's unbiased on average. And because of all this going on, we've got a plus misestimation in one direction if we don't stop. We've got underestimation in studies if we do stop. What does that say about bias overall in studies that have a rule or a protocol for interim analysis like this, particularly looking at futility? Okay. So that's what I'm going to show you a little bit of theory about, and then, as I said, we'll look at the literature. So this is rather like what we did yesterday, but now in the context of futility. So we're going to actually look at some expressions for the underestimation in the studies that stop early, overestimation in the studies that do these interim analyses but do not stop. We're also interested in the probability of stopping like this, of course. That's an important administrative question. And we'd look at overall bias in studies with a stopping rule. So we can again set it up numerically to evaluate all of these things numerically for some realistic scenarios, typical sample sizes, for example, and then we can actually look at some examples in the literature. So is everybody clear up to this point what the setup is? Anybody have any comments or questions? Burning issues? Smoldering issues? No. Okay, good. That's good. So as I said before, one of the main tools that we have in this context is at the point of doing the interim analysis, we calculate conditional power. And that is the estimated probability that if we were to go to the end of the study and complete all the follow-up on all the patients with the target sample size, and conditional on what we've seen so far, hence the name conditional power, and that's an important distinction, the probability that the result would be statistically significant. So in other words, what are our chances if we keep going? That's the crude way of putting it. What are our chances of a good result or a significant result if we keep going at this point? Now, unfortunately, there's a funny saying, you know, it's very difficult to make predictions, and this is a prediction, a probability of the result being significant. It's very difficult to make predictions, especially when the future's involved, right? And it always is. Right. I think it was Yogi Berra, you know, the famous baseball manager. He was the one that came out with stuff like, it's deja vu all over again, that kind of thing. So, okay, anybody awake? Okay, that was a joke, but you don't have to laugh, actually. Okay. All right, so the prediction into the future is difficult, right? And what we require to do in this situation in particular is we have to make some assumptions about what's going to happen if we go forward to complete the study. And in particular, what do we think about the future data? So the current situation is we designed a study with a certain delta. We were hoping for a mortality reduction of 20%, right? That was the plan. Now we've looked at the interim data and it only shows a 2 or 3% reduction in mortality, much less. So what do we think is going to happen in the future if we keep going? That's the big question. So we don't know, of course, but there are a couple of reasonable things that we could do, and a third one that people do occasionally. So the major two are here. The first option is we'll assume that at the beginning of the study, with our plan and our protocol, and in particular the delta, the treatment effect that we imagined, the 20% value, for example, we assume that that is actually correct, and that it's just bad luck and chance variation that has caused this disappointing result in the interim data. Okay? So we stick to our guns, right? We had that protocol, we had months of discussion, we put it into the grant, the protocol, and we got funding, and we've got all this money to do this study, and by golly, we're going to stick to it, and we believe that value of delta. We had good reason to put it in there, and we're going to keep it. So that's what you could do as option one for your assumptions. Option two would be say, well, maybe we weren't so sure about that delta, and now we've got a reasonable amount of evidence at the interim analysis that it's actually smaller. The effect is going to be smaller than we think, but there's some uncertainty about that. So the second assumption would be to assume that what we've seen up to now, the current trend at the interim analysis, that would keep going into the future. And so what's the probability that we would have a significant result at the end under that scenario? Okay? And in fact, option two there is very Bayesian because it's using the prior information up to the date of the interim analysis. So we're using the Bayesian approach to think about the future, and we're saying, well, we believe that the future will be very much like the past. Now, there could be other information that comes in, of course. You could be, for example, looking at changes in the clinical presentation of cases over time. The disease might be becoming more or less severe, for example, in presentation, and that could carry some implications about what you expect for the treatment effect. Okay, so there could be other things going on that you put into the decision now about what you think for conditional power, and in particular why you think option one or option two might be the best approach, or perhaps something in the middle. The third one is sort of a theoretical option, and I'm not going to really talk about it in any detail, but some people would say, well, particularly if the effect is negative, at the moment it's experimental doing worse than worse than control, the wrong direction in other words, let's put in a null hypothesis at this point. Let's imagine that really there's nothing happening, and what is the conditional power under that scenario? I personally don't like that one, and other people haven't used it very often, but it sort of exists out there in the methodological literature. But I'm not going to say any more about that one. Obviously, if you do assume there's zero effect, you're not going to have very much power at the end. You know that because it's zero. Pretty obvious, right? Okay. Now, once you've got this conditional power value, you need a decision point, a threshold about the conditional power to make the decision about stopping. And this is a little bit arbitrary, but typical values that people have used have ranged between 10 and 20%. Okay, so if your conditional power is that low, 10 or 20%, that means you've only got a 10% chance, for example, of showing a significant effect. That would be a signal to stop. On the other hand, if it's 30% or higher, for instance, you might say, well, we're still in there with a chance, so let's keep going. So as I say, it's a little bit arbitrary. Once again, it's a very good idea to have this in the protocol, to think it out ahead of time, right? So that it's not a rule, but at least it's something you wrote down at the beginning before you actually had the data to kind of interfere with your thought process. So it's a really good idea to decide on this threshold. And I think most people have been in that range. Many of them, I don't know why, 15% seems to be the most common value. So conditional power 15% or more in order to keep going. And in the methodology, what we need to do then is once we've chosen that threshold, we have to find the threshold value, the corresponding value of the test statistic, the Z value, for example, that would correspond to that, and also the analogous or threshold values that go along with that on the treatment effect. So in other words, how big a treatment effect do we need in order to keep going? And then the probability of stopping under these various scenarios, particularly those two main assumptions about the future data. And then we can estimate, once we've done that, we can estimate all these quantities that I mentioned before. How badly do we estimate the treatment effect in studies that stop early? How badly do we estimate them in studies that do not stop early but do that interim analysis? How much bias is there? And the probability of stopping. So those are all the ingredients that you put into it in order to estimate those quantities. Okay, now I won't go into the details. This is a nap time for people who don't like algebra. Okay, but this is basically what the conditional power looks like. In English, what this is saying is that the conditional power, based on some hypothesis about the treatment effect in future data, so that's where you plug in either the protocol value or the current value of the treatment effect, for example. So the probability of of the significant result, given what you say about future data, is the probability that the test statistic, a Z statistic, and this is in general, we might do a number of these analyses, analysis K is greater than the critical value or the threshold value, building in that alpha. Here's Dr. Ayer's main point, the alpha spending, that's where you put it. Probability that the test statistic exceeds the critical value, given what you've seen about in the data so far, and given what you assume about the future data. Okay, so it's just a calculation of that, and it's essentially based on the normal distribution once again, and so we've got this estimate of the treatment effect so far, and we have a standard error associated with that, and we can calculate everything as a result. So as usual, just to keep things simple, you can generalize these, of course. Assume we've got two randomized groups, just an A versus B comparison, and we assume that we have equally spaced analyses. That also makes life simple, so we might plan 2 or 3 or just one analysis, but equally spaced along the way for interim analyses. And once again, we don't have to worry about the standard deviation because that's a scaling issue. It doesn't affect the general picture, so we just arbitrarily put standard deviation of 1. So it's like a standardized effect. And I think I'll just skip over the next one, but that just gives you a little more detail on how to calculate it. And you can see that what comes in terms of the information fraction is right here. This T is the information fraction. That's telling you about the proportion of data out of the total that you have already observed. The information time, or the information fraction as referred to. So, some numerical results. We put in a range of parameters that are corresponding to, what you think of as reasonable scenarios for typical trials. So we could plug in a true effect size. This again is in standard units, standard deviation of 1, going from 0, no effect, up to 1, which would be a very big effect. And most usually we're working in the range of, I would say, 0.2 to 0.5 would be typical values in practice. We can plug in the alpha level, the alpha spending level, so we can put in 0.05 as usual. We can also vary the power, and we actually used different effect sizes here. These are typically regarded as a small effect, 0.2 of a standard deviation, 0.5 a moderate effect, and 1 is a big effect. So we looked at those 3 possible scenarios. Here are the 4 items that we calculated for all of those scenarios, and we did that under the 2 hypotheses, either assuming that the design effect was correct, the design is what's in the protocol for your delta, or having the current trend as the assumption of future data. And we also looked at 1 or 2 interim analyses. We actually cranked those out numerically. So here's one of the typical results. So this one, for example, is how much you underestimate the treatment effect if you do a futility analysis and you stop. Okay, so you actually stop. So these are actually all negative, as you expect, right? Remember, this is the random low phenomenon, right? If you stop early for futility, you're going to underestimate the effect typically. And you can see that the amount of misestimation gets worse if the true effect is bigger. So the x-axis here is the true effect, and you will more badly estimate that effect if the true effect is larger. Now, on the other hand, we do know that a compensating effect is if the true effect is bigger, we're not likely to have this happen, right? We're more likely to go in the right direction and find it correctly. So in other words, if there's a positive effect of treatment, a big positive effect of treatment, it's much less likely that we would actually stop for futility. Get it? But if we were in this situation where the true effect is small, then it's more likely that we would stop. But there's then a smaller misestimation problem. And how big is this problem? Well, you can see that under these various scenarios, so we've got the blue lines are what you get if the design effect is correct. That's what you had in the protocol. And the red lines are what happens if you assume that the current trend is going to continue. So you can see the red lines are actually slightly better, which is good news. And then these various types of line reflect whether you have a small, a medium, or a large effect. So there you have sort of the range of possible results. So they go from, depending on which of these you look at, they go from a very small effect up to something that's quite important. You know, one standard deviation change is what you call a big effect, and you'd be misestimating by that amount. Okay, everybody clear on what we're getting here? So it's a very similar situation to what we had for stopping for benefit. In fact, the most serious problems are when you do actually stop. Yes, did you have a comment? Yes. Well, what I said was if the truth is big, if you've got a large value of mu, this true treatment effect, let's suppose that you had a 20% reduction in mortality. Let's suppose that's the truth. Then that would be a situation where you would be quite unlikely to stop for futility. It's less likely that the early data would be in the opposite direction or showing little effect, compared to if you had a smaller planned delta. Right? So if the true effect was only 2 or 3% reduction, then it's much more likely that you would stop for futility because it's looking small and disappointing. Right? The truth would tend to prevail on average, and the extreme situations where it's looking like futility are less likely if the true effect is actually beneficial. That's what that means.
When your sort of assumption is higher effect,
yes.
Sample size will be less.
Correct. Yes, that's right.
So the patients in your interim analysis will be less.
Yes, that's right. That's right.
Ultimately, that will compromise the power.
That's right. That's right. So obviously you should have planned the study with good enough power for the final analysis. Remember, the power relates to the final analysis at the beginning anyway. And so if you do an interim analysis on a small study, those are more often where the issues get more critical, right? You're more likely to make a mistake because you have less data. We saw that yesterday, right? If you have a big study, then the chance of making a mistake on it is smaller. Yeah. Yes. Do we have the microphone for people? Thank you. Yeah, go ahead. Yes.
Only the planning of interim analysis will be one of the main reasons for making observations. So the planning of interim analysis is one of the main reasons. Is there any other reasons for having misestimation as well as that causes for stopping as well as leaving the
Is there any other reason for misestimation? You mean some other reason why the results are disappointing?
Other causes, yeah.
Oh, sure, yes. I mean, exactly as we discussed yesterday. This is just telling you about the statistical properties of what you're seeing, and it's providing you with some information, some evidence about whether you should stop for this reason. But if you think that the results are looking disappointing for some other reason, not just random variation, for example, let's suppose it's a quality of life outcome, and you have a really terrible scale, right, with a lot of measurement error involved. Well, that could make it look like the two groups are more similar because you simply can't pick up the signal of the benefit. So that would be a reason why the results are disappointing, completely separate from just random variation like this. Okay. So yes, you want to look at the whole picture. It's an important decision if you're going to stop. Whether you stop for benefit or for futility, it's exactly the same situation. So you have to look at the whole picture and think about other reasons for what's going on. Does that answer your question?
In that scenario, so what is your suggestion to calculate the power calculation, the reverse power calculation?
What is your situation to calculate the...
See, the thing is,
what do you
we
mean
planned interim analysis like 33% of enrollment, 66 subsequently.
Yep.
So maybe this is correct or not. According to my enrollment ratio, allocation ratio, I planned my interim analysis like 33% of enrollment as like according to this, some situations. If it is not so, suppose if I am facing a very slow enrollment rate, so how can I plan? And if this is causes, obviously this is deals with insufficient number to calculate that particular interim analysis.
Right. Okay. Well, the particular reason you introduced there was slow recruitment, which actually is also called futility, right? But that's more administrative futility. You haven't managed to find enough patients to keep going with the study at the rate that you had planned. That is a very different issue from this, right? So you would have to decide, well, given now, let's keep it simple. Let's suppose you planned 100 patients and you've now got 50, but it's taken you ages to get that far, right? It took you longer than you thought it would to get to this interim analysis halfway. You now have to decide if you're happy with that. You'll have an estimate that's got a wider confidence interval than you'd hope for because it's limited sample, and uncertain evidence about the benefit or futility. You have to then decide, given all of that and given your concern about enrollment of patients, whether to go on. Right? So that would be a particular example of another factor that would come into the decision, the difficulty of enrolling patients.
With conditional power, you have to calculate both for stopping for benefit as well as futility, or only for the conditional power. Do we calculate only when we are thinking of stopping for futility or even for benefit?
No. Conditional power is usually calculated in this situation for futility, not for benefit, because if the early data show a promising effect, everything's going well, and presumably if you did calculate conditional power, it's actually going to be higher than in the original design. So it's kind of, you could do it, but it's not really necessary. You know that the power is satisfactory and possibly even much better than you had planned originally. So the main use in practice would be in this situation for futility. Yeah. Yes?
My doubt is, we are saying that there is misestimation in studies that do not stop early, whether for benefit or for futility.
Well, actually, that's not true. This is misestimation for studies that do stop.
No.
Yes, that stop. Yes, okay. Right. Previous one. Where did you want it? Right. Okay. Yes, there. We're talking about underestimation in stop studies at the moment. So what's your concern?
No. For example, in the previous, yesterday we saw misestimation in studies that do not stop early.
Right.
And interim analysis for benefit tend to underestimate.
Right.
And today we are saying they tend to overestimate.
Correct.
But why is that so? Because they can always be near the true effect.
Were you here at the beginning? Were you here at the beginning of the talk? Did you come in at the beginning of the talk? Did you arrive at the beginning of the talk today? Because I talked... Pardon? Slightly late, so you may have missed it. Okay, let me go over it again, because other people may have missed it. This is the mirror image of what we had yesterday. When you stop for benefit, it's the random high. And you're going to overestimate if you stop. And correspondingly, if you have a random high, or looks like high, but you do not stop, That's underestimation. Okay? Here, we are stopping or possibly stopping for futility, which means it's a random low, right? And we just argued, and I think everybody nodded their head, yes, that made sense. If you stop at that point, it's a random low you have underestimated in stop studies, and there is a corresponding balancing effect for studies that do that interim analysis but do not stop, hence overestimation. So it's the opposite of when you think you have benefit. Is that clear? Yeah. Okay. Just turns it around. Did you have a question? Yeah. No?
Yeah, I think one thing we are missing in the 2-3 days is before doing any sort of analysis or stopping or this, you should look for a methodological explanation. That is a prerequisite for this analysis.
Oh, absolutely. Of course, yes. I mean, we went over that yesterday in the context of futility, of benefit, all those other reasons that you might want to consider, all the methodology questions. You have to do it all again, of course, here. Absolutely, yes. They all apply, yes. I'm not ignoring them. Yes. Can you take the microphone, please?
So, can we go to that figure?
Next one?
Yes.
Okay. Yes?
Sir, here, like, with regard to design, there are 3 values, 0.1, 0.5 and 1. These are actually effect size or what?
It's the planned effect size.
Planned effect size.
Yes.
So, with regard to graph, what I conclude is like, if the true effect size, if the true treatment effect...
The true treatment effect is on the x-axis, yes.
If it is less and our design effect size is also less, then the chances of error is less.
Yes.
Is it right?
Well, not the chances, but the amount of error. The amount of error if you stop is less, that's correct.
Less.
Yes.
And similarly, if our effect size assumed is higher, that is 1, and the true treatment effect is like higher, then the chances of error are again low.
No, it's not the chance of error, it's the amount of error.
Amount of
if you
error.
stop, it's not the chance of error.
Amount of error.
The chance of error is the chance of stopping.
Okay, sir. Thanks.
Yeah? Okay, good. Yeah, so you can see down here, it doesn't really make a lot of difference. Among these groups, for example, the red groups are fairly closely spaced. So you could say that the planned effect size doesn't seem to make much difference under the current trend design. It makes more difference under the, the current trend design. The red ones are under the current trend. If you assume things just keep going, the value of the alternative hypothesis value isn't too important, but it's more important under the blue ones with the design hypothesis. So, but I think you just need to look at this qualitatively and say there's a range of possibilities here, and it depends on exactly what you planned over here with the effect size, and also which hypothesis you believe about the future data. That's a critical one. Okay. This is, what's this one? Okay, I'll perhaps spend less time on this one, but this is about the effect on the overestimation for studies that do a futility analysis but do not stop. So again, you can see that there's a little effect of power here. It's less of a problem if you have a large treatment effect, which is what you would probably expect. You can get the problem down, the overestimation problem down, if you have more power, but it's not huge. Numerically, these aren't massive, except perhaps in the few cases where you've got a very small effect, and you perhaps don't have superpower. So those would be the worst case scenarios. Over here, this is under the design hypothesis, and you have a bit more of a problem there. So you're looking at 0.1, 0.2 of a standard deviation. So it's actually numerically much less of a problem than the ones that do actually stop. But there is a range of possibilities here as well. So the take-home message is going to be actually, it's very similar to what you had for benefit. It's actually the studies that do stop where you get the greatest degree of error in the estimation. Okay, and then overall bias. This is a terrible looking graph, but this is how it is. We've got the design hypothesis the current trend hypothesis and different sizes of effect. This is the overall bias that you put into the protocol by having a futility rule. You can see it's negative, so there's an overall bias, but it's relatively small. Even the worst case scenario is only about 10 or 12%. Okay? And it turns out there's an interesting theoretical result that there's actually a maximum. You can actually find out what that is. So here are these maximum, the upper bound for the bias under these various scenarios. So the worst case is actually if you plan for a very big effect, you're running the risk of a 10% underestimation overall. So it's not too bad. Okay, I'll skip over this. This one talks about if you have two interim analyses, so it's a somewhat similar picture with some variation. If you're interested, you can have a look at the detailed paper on this. Here's the overall bias again under the two assumptions, and so on. Okay, let's give up on that and move on to the next part of the session, where now we've seen the theory. Let's have a look at what's actually going on there in terms of the literature for trials that have actually stopped. So, to orient you, we've seen already that having a futility stopping rule can lead to substantial misestimation of the treatment effect, particularly in studies that do stop. But now you want to find out whether this really matters in practice. So it's very similar to what we did yesterday by looking at samples of actual studies. So this is again part of what I referred to as the stop it studies, the stop it group, so do stop it. And what we did within a bigger sample of all sorts of trials which had been identified in general, we found a group of studies that had stopped indeed for futility, and I'll show you a little bit about the literature search in a moment. And we went into those studies and pulled off a whole lot of information such as that. What's it about? The clinical intervention. What did they plan for the study? What was the actual treatment size? And so on. Sample sizes, study power. Whether they actually thought about this beforehand, whether the interim analysis was thought about ahead of time, how many interim analyses that were actually done, if they did a futility analysis in particular, and what criteria or threshold they would use to define futility. In other words, how bad would it have to be in order for them to stop? Did they say that at the beginning? Was the futility analysis itself at least part of the basis for stopping? And then, interestingly, we were able to find for some studies the conditional power because they reported it, and in some other studies we were able to use the data that they had to calculate conditional power ourselves. That was a lot of work, but we managed to do it. So I'll show you some of the results for that. So we did the calculation of conditional power, making those two alternative assumptions that I mentioned just now. One was that the current trend would continue, and the other was that the study design treatment effect would be retained, that we believed that it was right in the first place, and we hang on to it and assume that it will remain in place for the remaining data. So how strongly do you believe your protocol? How much do you believe what you thought before at the beginning of the study, and how much has your opinion been changed by what you've seen in the interim analysis? And you can go one side or the other depending on your thinking. Okay, so here is the, oh sorry, this is a little dim. I hope you can read it anyway. So this is how we did our analysis or our extraction of data. There was a systematic survey of studies in group 1 here through Medline and Embase to look at trials in general, and we also have a set of studies through what's known as the DISCO study. It's a related group to the Stop It study where they actually have protocols as well as published papers. So those two were combined at the end here. So we, on the left-hand side in the original sample, we had almost 2,200 samples that were, or studies that were obtained and screened, and most of them had to be thrown away because they weren't randomized trials, or they didn't talk about stopping. They didn't talk about discontinuation in their abstract at all, so they got dumped at that point. We had then left on this side 280 trials that were discontinued, where we looked at the full text, and then of those 280, 249 had to be thrown out because they were not superiority trials, or they were not actually stopped for futility. So just for simplicity, we limited our attention to superiority trials. You can go through this kind of exercise for non-inferiority and equivalence trials, but the calculations are a little different, and we didn't want to muddy things too much. We thought most trials would actually be about superiority. So that was our decision on that. On the other side, we had just more than 1,000 trials where they had been approved, and this was basically to follow up and see what happened to those studies, whether they were actually executed and whether they were reported. We looked at them through all of the information available for those trials as being followed, whether they had actually stopped early, and we found another 37 that were explicitly stopped for futility. However, among those 37, 19 of them were not published, so we couldn't get really any sensible amount of information. So that's an interesting group, because it's quite a significant fraction there, so which is 19 out of 37, that's just about half, right? Which is suggesting that this happens a lot of the time, and people give up on studies but don't even tell you about it. And that's a problem, of course, because that's publication bias, right? And there's been a very strong recommendation that people should always publish somewhere so that it's on the record, because negative results are results. Right? That is a result. So anyway, in the end, by combining these two sources, we were able to actually find 52 studies that were superiority trials that had been stopped for futility, and they were reported in 49 articles, but we're actually talking about 52 different studies. Sometimes there were more than one trial reported in the same paper. So that's what we're going to be talking about now, the 52 studies that we actually looked at in detail. Just to give you a sense, and I'm sorry this probably won't show up very well on your printing because it's small, but this is just to give you a general sense of what we extracted. So this first table here tells us about the authors, just so we could keep track, what the subject was and about their futility analysis. So the subjects here, you can see it's all over the place. Retained placenta, lung cancer, myocardial ischemia, thrombolysis, and so on. So it's a very wide range of clinical investigation areas. Then the next thing we got was IA's interim analysis. Was an interim analysis for futility planned, and what was the number of interim analyses planned? So we have yes, there was one planned, don't know, didn't say, yes, one, and so on. So here's one with 2 planned, and so on. What was the basis for their futility stopping rule? A lot have not stated, we don't know. Here's one, it says the one-sided p for both co-primary endpoints, so there were 2 endpoints here, both of them had to be 0.5, so that's the p-value. For both of the endpoints had to be bigger than 0.5, that was their rule. Not criticizing, that's what they had. Some of them had defined threshold value for a test statistic, for example, or this next one they had a threshold effect size. That was, so they would say, well, if we observe less than 5% difference in mortality, we're going to stop. Okay, that kind of thing. And here's the number of actual interim analyses for futility. Mostly 1, occasional 2. Sometimes it was done annually, and we don't actually know how many there were. That was the best we could get out of it. And there are a few down here with actually 0. So they stopped for futility, but they didn't actually do an analysis, which is a very peculiar situation, but there you have it. So this is just the first table of first set of several, just to give you a sense of what these studies looked like. So that's the first 19 out of the 52. So on that, to summarize, we found that out of the 52, that's close to 50 is a good way to remember it, but about 75% had actually planned an interim analysis, which is good news. That's not a bad rate. Not planned, 5 of them, and so these studies did stop, but they didn't plan to stop. Okay, so why did they do that? Well, they said things like this. The patients were apparently reporting no clinical benefit. Okay, well, that's good. Seems like a good reason, but they should have thought of that ahead of time. This one was because of funding difficulties. They were having trouble keeping the study going, and so the Data Safety and Monitoring Boards, interestingly enough, requested that a futility analysis be done. So it wasn't planned, but it was done. This one, there was an interim analysis that was planned for benefit. That was in the protocol, but it turned out things had gone really badly, and they also evaluated futility, and they stopped for that reason. So they planned to look at benefit, but they actually stopped for futility. Slow patient recruitment, so that's more administrative futility rather than statistical futility. And another one here, publication of disappointing results in another related study. So they felt they couldn't continue in view of the evidence that was published during the conduct of their own trial. They couldn't continue, couldn't justify that because of what they'd seen elsewhere. There was a group of them where it was not stated if it was planned or unplanned. You know, what do we do about that? That's a problem. And the most common number of planned and completed interim analyses was 1 in 20 out of the 52 trials. But the problem there is we don't know if they might have done more if they had not stopped. So there's a kind of truncation there because the study stopped, and we don't know. They might have done more. So, and that was usually not very clear at all. What were the criteria at the interim analyses? This a priori means at the beginning, previously stated for stopping. More than half of them had no stated criterion. More than half did not say in advance what any criteria would be for stopping. That's really a stunning statistic, isn't it? If you're into this business, it's a very major thing to stop a study. They didn't tell us what the reasons for stopping it would be. That's pretty disappointing. And they presumably did have reasons in mind, they just didn't tell us. About a quarter of them did have a formally defined threshold value, either as a test statistic or an observed effect size, and those are effectively equivalent because one corresponds to the other. So that's good. They did pre-specify a formal threshold value. 5 of them, so 10%, did actually say they would calculate conditional power, and that would be the basis for stopping. 4 of them said they would use a p-value. Ooh, I hope that's not one of you. We know how bad p-values are, right, for conveying evidence, but 4 of them said they would use that. And 1 of them said they would use a futility criterion, but they didn't say what it was. They just said they would use a futility criterion. Who knows what it actually was? Okay, now we go on to table 2, again, which may be a little bit small for you. This is something to do with the selected statistical features. So what we find here is this is the stuff that we were able to extract. And this is what you might have done, some of these things you might have done when you reviewed your paper last night. We'll be hearing about that in a moment. Okay, so what did they plan for their target sample size here? What was their type 1 error rate, the alpha? Was it 1 or 2-sided testing? And you can see there's quite a range of those. And the sample size is, by the way, hugely variable. Look at this. What's the smallest one I can see? There's one down here with 58. I think that's not even the smallest one. And another one here with 1,300. So big range of study sizes. What was the planned study power? What kind of endpoint did they have? Was it binary or a continuous one or hazard ratio, for example? What was the outcome variable? And again, huge range of clinical outcomes here. Manual removal of the placenta, brain metastasis, ischemia, survival, HIV infection, viral load, set points, and so on. So it goes. What was the null or the control value? That's what expected response rate under the control treatment. And what was the design hypothesis? So this is telling us about the delta. What was the expected outcome in the treatment? So here we've got one with 40% relative reduction Here's one with 15% absolute reduction. And then this one, for example, relative reduction on HIV-1 infections. And this is an absolute value for the viral load set point. So you have a mixture of them in that particular study. Okay, so it's quite a mixture of things to deal with analytically. And then the last table here are the details of this selected group of papers. So we found the information content, or the fraction, or the sample size, varied in the way people reported it, for planned interim analyses. So this first study is saying 75%. They would do an interim analysis at 75% of the target sample size. Okay, this one down here, it says they would do it at 33 and 67. So they're doing 2 interim analyses, or planning to, at 1/3 and 2/3 of the study. Then we have the actual percentage of information at the last interim analysis. So the one I just referred to stopped at 2/3. They did an analysis at 1/3 and kept going, but at the second one they stopped. Then we also found out if they were just reporting a futility analysis, they said they did one, or did they actually claim futility without telling us any details. So in other words, did they give us some details about their futility analysis or not? So a lot of them just claimed it, and some of them actually reported it in terms of terms of conditional power or some other evidence. Then, interestingly, the basis for stopping, continuation would not alter the interim conclusion that the intervention was effective. The basis for stopping was, quotes, futility analysis. That was all some people said. They did futility analysis. Lack of effective evidence, low conditional power. So people expressed it in all sorts of different ways. This is the main result, the observed effect size. So here, for interesting one, 40% versus 33% absolute, which is actually, not a trivial difference in the responses, but the p-value is 0.53 and they decided to stop. Conditional power was actually calculated here in this study, so they found, and this is, by the way, under the 2 alternative hypotheses, right? Under the design hypothesis and the current trend hypothesis, you get the 2 values of conditional power. So good for them, they did find it, and it's very low, extremely low, and so they decided to stop, obviously, because of that. And a further interesting question is whether they did more analysis after the last planned interim analysis. Because as we mentioned yesterday, there are always patients that are coming along. They're always in the pipeline. So you may, for your final report, end up with more patients than you had planned for at the interim analysis. So to the extent that happens, that you get more patients, it's saying that actually the interim analysis and stopping does not prevent that many patients from receiving an inferior treatment. There are still more coming in. So you need to think about that as the impact, the possible impact on the whole study in terms of preventing people receiving the inferior treatment. So you can see that for most of them, the answer was no. So there was no further analysis. They did the interim analysis and that was it. Yes, that's what you got. Other ones it wasn't clear. Some of them was yes, we did have additional patients that came in. Okay, now to summarize some of those things. So, first of all, in terms of the timing, when did they actually plan to do these interim analyses? And most of them did it, or more than half did it, as a percent of the planned number of patients or events. So they might say, I plan to do it at 50% of the patients. Most of them, or well, the largest group anyway, did it at 1/3 or 2/3 of the sample. It's a very common decision. And some of them did at specific time points, specific dates, or annually. Okay, rather than as a percentage of the data. But a big group here, no idea, don't know, didn't tell us. And this lack of reporting is a common theme, not just for this particular investigation, but it's a big problem. Why did they stop? So again, this is all out of 52 that we had. They mentioned futility somehow. And by the way, these multiple answers are possible on this one. So they somehow mentioned futility when they were discussing their disappointing results. So about 1/3 did that. Some of them expressed it as a belief, about what was going to happen. They felt that the results probably wouldn't change if the study continued. How they know that, I don't know. They said that the trial had already failed to show treatment benefit. That's an interesting statement because they're looking at, incomplete data and uncertainty, but they feel that they've got good reason to stop for that. Another one was interesting. They said the final results would not be statistically significant. They actually knew that. So they were very good at prediction because they'd obviously visited the future already. You absolutely cannot possibly say that, right? You don't know. About 20% reported conditional power. That was great. And a small group of them actually said something about a boundary that had been crossed, either in terms of effect size or through one of the stopping rule boundaries. But many of them had other verbal summaries of the outcome. The outcomes didn't differ. There was insufficient efficacy. The intervention was inferior. An interesting one, conditional power was nearly zero. So apparently they computed it. They didn't tell us any details. The study had almost no chance or was unlikely to achieve statistical significance. Or, here's another interesting one, the impossibility of demonstrating efficacy. So those people have visited the future as well. They know what was going to happen in the rest of the study for sure. And another rather curious phrase, presumed futility. I guess they're recognizing there's uncertainty about the future, but they think it's futile. Now on the conditional power, sometimes it was reported by the investigators, which was good, but only in a minority. There was another group where we couldn't do anything really because there was not enough information in the paper. But for about half of them, we were actually able to calculate conditional power ourselves. When I say we, I'm talking about students. Students come in very handy for this kind of thing if you have them available, because this is a lot of work. So you can tell them what to do and send them away, and they can get a thesis out of it. So I'm joking. We actually had a very good graduate student, who wrestled with all this stuff for a very long time and gave us a lot of the results you're going to see. So when we calculated conditional power ourselves, this is in the group of the 25 where we were able to do it. The big message here is that the conditional power depends very much on the hypothesis that you use. So if you use the current trend hypothesis, that is, you presume that everything's going to continue in the way you've seen it already, even though it's uncertain data, then most of these studies, more than 90%, have conditional power less than 15%, which was the threshold, remember? So it's a very low chance of a significant result. So on that basis, they were right to stop, right? If the conditional power is really low like that, then they were probably right to stop. A couple of them had slightly higher conditional power. There was one I don't remember the exact number, but between 30 and 50%. However, remember all that work that you put into the protocol and how much you argued about what the delta was and how much you were hoping for as a treatment effect. Okay? Well, if you retain that, if you believe yourselves a year ago, you get a very different picture. And in fact, many of them here have quite significant, or quite substantial, I shouldn't use significant, quite substantial conditional power. So a lot of them, if the design hypothesis and the protocol was correct, actually have quite a good chance of showing a significant result. And the highest value that we found was 73%. So that's quite a surprising finding, that there's actually an argument for many of these studies to have continued, at least on this basis. Okay? Right. And then the group of, smaller group of studies that reported conditional power directly, so we didn't have to do the calculations. And just to save some time, we believed them. We didn't check their calculations because each one of these was, an effort in itself. So if they had reported something, we actually used that value. Only 2 studies told us what the hypothesis was about future data. Now, how useless is that? You tell me what the conditional power is, but you don't tell me what the assumption is that is crucial to that calculation. It's what are you assuming about the future data? So only two studies did that out of 11. Terrible, right? Well, let's press on. 5 studies gave us conditional power numerically, and it was less than 15%. 2 gave us numerically, and it was in a sort of moderate range. And 2 gave us a conditional power, but without an exact figure. They said it was less than 30% or less than 60%, and both of those were under the current trend. Those are the 2 that actually did tell us. And 2 reported descriptively. These are the ones that said there was no chance or nearly 0, but they didn't give us a numerical value. I'll just keep going, and then we can have some discussion when we've looked at all these results. Then the question of did the study really keep going after that interim analysis when they, quote, stopped? Well, in about half, a little less than half, accrual stopped immediately, and there were no further patients reported in the final analysis. But another group, almost the same size, had more patients included. That's presumably because of the pipeline, that there are patients still under follow-up. And 8 where we couldn't really tell what had happened. But asterisk here, there was actually one study where the final sample size exceeded the original target. So that interim analysis, or those analyses, had no impact whatever on stopping the study, in effect. They said they stopped, but actually they ended up with a bigger sample size than they planned in the first place. So if one of the goals was to stop early, how badly did they fail? They even kept going beyond the point when they'd originally planned. Okay. And many of them, it was a substantial number of people in the final analysis that had not appeared in the interim analysis. Okay, so summarize that then. Here are the main messages. I think that based on those conditional power calculations, that stopping for futility was reasonable in many of the cases, but only if the current data trend is accurate. So if you think that is the best estimate of the treatment effect, then you're probably right to stop. The conditional power usually turns out to be very low. But sometimes it's rather questionable if the original protocol is retained. So that's a critical question for you. How much do you believe that the original protocol based on everything you knew at the start of the study? Unfortunately, reporting's pretty bad. The reporting of the rule itself or how they made the decision to stop is often missing or vague. And sometimes, of course, we also worry about the studies where we didn't even get them into the sample because they didn't even mention that it was an early stop. Right? There are many of those studies where it never comes through. They just say, here's our study, and you don't know the fact that they actually had stopped early. We don't have any information on those studies, of course. It's unclear if the interim analysis was planned ahead of time, unclear if other interim analyses might have happened later, and many of them claimed futility, but exactly what criteria had been used was often missing. Only a few actually calculated conditional power, and many of them had substantial conditional power, especially under the design hypothesis. So it's actually about a quarter of those studies had conditional power more than 50%. And, on the basis of a coin toss, you should keep going, not stop. Okay, and then just a couple more slides, and then I think we're done on this section. Some related issues. We haven't talked about meta-analysis, but it's the same problem as we had yesterday, that truncated trials may actually have large weight in early meta-analyses and be influential as a result. Sort of politically and the way science and funding works, if you accept the result of a truncated trial at face value, there may be some freezing that goes on whereby confirmatory studies never happen or are much less likely to take place. So you might have arrived at the wrong answer through an early analysis, and you affect the subsequent course of research in other places. Underreporting, the actual usage rates of stopping rules is greater than it might appear, as I mentioned, so there may be other studies that did stop early, but they didn't even tell you they had a stopping rule. And the last point here is just that although we keep calling them stopping rules, they're really guidelines. And there are other reasons why you might want to stop or not stop. And there are certainly many examples, and I've been on data monitoring committees, where you overrule the findings from the interim analysis. In other words, the interim analysis might tell you to stop, but you keep going, or vice versa. And final conclusions. Studies are difficult to interpret if they don't tell you all of what they were planning and what they actually did. When they do stop early, it's very important to identify why, how they declared futility, and the assumptions particularly about future data. If they don't tell you about those, then it's really hard to know what the impact is on the estimated treatment effect. So you may have a very bad estimate, but you really can't tell. So this is the faint hope that we're putting out. This, by the way, is all, this later stuff is all in a paper that's currently under review, and I'm very hopeful it's going to be accepted very soon. But our sort of recommendation that we put in some detail is that we should really improve the reporting of these stopping rule protocols and how they were actually executed in practice. And because this is work in progress, I did just want to thank or acknowledge the colleagues that have worked on this. This person, Heeden Han, was my student who's now working at Mount Sinai Hospital in Toronto. Dirk Basler, who's in Zurich in Switzerland, and a couple of people at McMaster, of course, Gordon Guyot, I've mentioned his name before, and another person, Matthias Brielle, who is in Basel in Switzerland. So it's been a big effort with a big team actually working on all of this stuff. Okay, so that brings me to the end of that little section. Does anybody have any quick comments on that? Yes, Jay? Yes? And then I do want to move on to the exercises. Oh, okay. Thank you.
The study which after futility analysis, power and retrospective power, conditional power analysis, went on recruiting patients. Have they given their power, conditional power in the data?
Well, okay. The issue was that sometimes you would have more patients in the final report than they had at the interim analysis, and the interim analysis was intended to consider a stop. The reason, quite often, that the two numbers are different is very reasonable, because you have people who have already been enrolled, okay, but they haven't had their outcomes observed yet. So it might be a year of follow-up, for example. So that person was enrolled last month. I have to wait quite some more time before I get his outcome, but that will get into the final analysis. What should absolutely happen, though, if you've decided to stop for futility or for benefit, there should be no more recruitment, which is the word you used. You shouldn't enroll any more people and randomize them. But apparently, at least in that one study, that didn't happen, because they kept introducing more people into the study. And you asked about whether they calculated conditional power at that point. I don't know, but I very much doubt it. If they didn't do it before, they're unlikely to do it now.
The second question is that when you do the conditional power analysis, there are two ways of doing it. One is
yes.
What are the event rates at that moment when you do the interim look.
Yep.
Another one is looking at what we have thought would be the event rate.
Yep.
Given that number,
yep.
What is the power? Should we look at, when I decide the proposal, I would have been very optimistic that the effect size would have been more, and therefore I would have decided the number. So I may not be very correct at the planning itself. But when the data started coming to me, when I do the interim analysis, I may be correct. That gives us a reality of what is happening there.
Yeah.
So therefore,
well, there is some evidence that says that there's a substantial difference between what people put in protocols and what actually turn out, and it's in the direction that you might expect, that things aren't as good as you'd hoped for, or at least they're not as good as you said they would be. So there is some game playing going on here. You know, when you apply for funding, you want to look optimistic and hold out the hope that you've got a large reduction in mortality or a big treatment effect. Because if you go in saying, well, we think it's going to be pretty small, that's less impressive as an application for funding. So there is some of that. But you are sort of shooting yourself in the foot, you know that expression, right? Because if you get to this point of an interim analysis and it turns out that way, you have to admit that, in fact, the protocol is not that accurate in that respect anyway. But you would like to think that studies do get funded on the basis of reasonable estimates of delta, right? That they shouldn't be completely wild estimates just to game the system and come up with a reasonable sample size. Oh yes, and I do have a video on sample size, a comedy video about sample size. And what we actually do in our grant applications is we put a range of parameters for, the response rate and the likely effect size, the relative risk, for instance. We put a range of them, and we say, well, we're reasonably powered in the middle, and it could go plus or minus depending on how you change those parameters. Yes. Dr. Tambu, I think, was next, so I'll have him. He's got a microphone already. He doesn't need two.
No. Somebody asked the question, if the interim analysis suggests we stop the study, and the funders withdraw funding, what happens to some of the patients who are just recently recruited and have not finished their follow-up?
I think normally there would be provision to complete the people that are already in the trial. If there are resources that are involved, they should be completed, and that apparently did happen because you have these extra patients that come into the final report. Are you talking, though, about a decision to change the treatment on those people?
No. The decision is to stop the study based on our futility. But what if the funder says, I'm stopping the funding abruptly?
I don't think they would. At least in my experience, I don't think they would do that. I think they would allow they provide sufficient funds to run the study to completion for the patients that they already have. Okay. I think so. Okay. Otherwise, you'd be in a very difficult situation, right? Yes. Okay, now there's a question there.
So what if you use an estimate which is midway between current trend and the design effect? Wouldn't that be a bit more realistic?
Well, that's up to you, and you could certainly do that.
I mean, is there any analysis that's been done somewhere?
Absolutely. Put a value of delta in that's somewhere in between. You could do that, and of course the conditional power will also be somewhere in between those two estimates. Use whatever value you like, whatever you think is reasonable, and if you have some good reason to do that as a compromise, sure, argue that case. You can calculate it for any assumed value. Yeah. Another question? Yeah.
Sir, I must say sorry because for 3 or 4 slides before you have shown that the current trend hypothesis and design hypothesis, there is a comparison.
Tell me when to stop. Keep going.
Before this one.
This one?
So,
yes.
So actually, I think I may not have understood what you have said. So I didn't get the idea of difference between two, because I thought of like whenever you design a protocol or do a hypothesis, so you at every point of time you will have a power of 80% or 90%.
Yeah, if that delta is true.
Okay, so at whatever this has been done, this conditional powers, these are point estimates, correct? At a given point of, say, like at that interim analysis, you have found that power, correct?
Conditional power, yes.
So this is according to the design hypothesis, correct? Or no?
Well, this is the design, and that's the current trend. Both.
Still, I'm not understanding it.
Okay. All right. Let me go over it briefly then. So you have the interim data, and here we're looking at situations where the interim data is disappointing, showing a small effect, and we can either assume that that will continue, right? So let's say we have a 2% advantage of treatment A versus treatment B. We would assume that that is the truth. What is the probability that we would actually find a significant result at the end? That's what you get on the left-hand side.
Yeah.
Okay? On the other hand, you could assume that the data we have now, well, it's 2%, it's disappointing, but maybe that's just unlucky, chance variation, the random low, and we stick to the protocol and the hypothesis we had then, and that's the design hypothesis, and then of course that's more optimistic. We're assuming that future data will be better, and we therefore have a higher distribution of power, conditional power.
But still that would have been 80%, sir, no?
What could have been 80%?
Design hypothesis, no?
Well, it was 80% at the beginning maybe, but now we have this data that's much less than what you had predicted. So your power has obviously gone down conditionally. It can't be 80% anymore, can it?
I will get you back on this probably, because I am still not understanding this.
Okay, so all right. Well, let me just try another way. The power is the probability that you will get a significant result at the end of the study, right? You start out and it's 80%, let's say. It doesn't have to be, but let's assume it is 80%. So that's the plan at the beginning. And that's based on an assumed value of delta, a 20% change in the response rate. Okay, now you go along and you're halfway through the study and, unfortunately it's not 20%, it's only 2%. That obviously is bad news, and it must have reduced the power, because in order to get to your significant result at the end, now for the remaining part of the study, you may actually have to do better than in the first half, right? Or even better than the original delta. You have to compensate for the bad results so far. So the conditional power, given those disappointing results, is going to be less than 80% and often a lot less than 80%, as you can see here.
Okay.
So the decision is, let's say you got one of these and arbitrarily, let's say you found the conditional power is 50% under the design hypothesis. That's the question. Do you want to continue? You've still got a chance, got a reasonable chance of finding a significant result. Do you want to continue on that basis?
Okay. Okay. And one thing, is this conditional power is same as futility indexes as being stated in many articles? What is the difference between futility index and, because I came up across some certain thing as futility index. I don't know what is that.
Sorry, I didn't quite get the question. The difference between conditional power and
futility index.
Futility index. I don't think I used that phrase. Okay. Futility is the general concept of stopping because you're convinced through the early data that not much is going on. It's not worth continuing the study. Okay. And we assess our level of futility, if you like, by calculating the conditional power. Okay. So if the conditional power is low, it means you have a very small chance of showing a positive effect in the treatment.
Okay, thank you.
All right. I'll take one more and then we need to move on because we're getting close to coffee time. No, she was next, I think.
Sir, just three small points actually. One, when we were thinking about...
No, you're only allowed one question. One question.
Right, sir. Okay, then I'll stick it to one point.
Burning question.
Okay. When we were talking about stopping trials early for benefit, we were focusing more on the alpha. But when we are talking about stopping trials for futility, we are focusing a lot on the power.
Correct. That's right.
So why is it?
Why is that? Okay. That's a really good question. I didn't really talk about it so much, but in fact this idea of controlling the type 1 error rate is still very much there in futility situations. If you have a protocol that says you're going to do an interim analysis for benefit, for futility, or for both, right, you would actually want to control the type 1 error rate as well. So the boundaries that you have to declare futility in particular would be very similar to the ones you have for declaring benefit, but you also would look very much at this conditional power, because the crucial decision is, do I go on or not? Okay. Right, that's the main question that you want to ask. As I said, there was an earlier question, why not calculate conditional power if it's looking good, if it's beneficial? Well, you could certainly do that, but the answer is obvious, because everything's going great. You actually have a really good effect, a good response. So your conditional power now is actually going to be better than you started. It's going to be more than 80%. Yes. So there's almost no point in doing that calculation. So there's a parallel between both situations, benefit and futility. You need the alpha control for type 1 errors, and you also could calculate conditional power, but it's a little bit irrelevant for benefit. Okay? All right. I'm going to call a halt there. Now we're just going to have a couple of minutes of amusement, and you can think about what you're going to say about your paper. And I will choose one of those papers in a moment, so beware. How do I get to... Okay. Yes, here we are. Now, I'm hoping this is going to work. Full screen. Right. And if I push this, I'm hoping this is going to work. This is a little video. There are a whole bunch of these if you want to look at them, and there's a whole bunch of them about p-values and all sorts of things. This is one where the scientist comes along and he wants a sample size from the statistician. Okay, a very common situation. So the scientist comes in, actually knows the answer about his sample size already, but he's just consulting the statistician just to make sure. So I hope the sound will come up. Let's hear.
I have a study, and I need to know how many patients I need. I think I only need 3 patients.
Okay, what kind of study is it?
I'm doing a lab study. Can I just use 3 patients?
That depends. What are you trying to show?
We always use 3 patients.
Okay, what are you trying to show?
I'm trying to show that drug A and drug B are better than only drug A.
How are you measuring if it is better?
We are looking at apoptosis. Can we just use 3 patients?
What kind of measure of apoptosis? Do you know how variable that measure is?
We always use 3 patients. That is what we have published before.
3 patients per group or in total?
Yes.
Okay, let's try something different. What type of measure are you using? And is this an in vitro study? An in vivo mouse study?
It is an in vitro study of patient samples, and we are looking at measures of apoptosis after treatment with drug A and drug B versus drug A and control. And drug B alone.
Oh, how many groups are you analyzing altogether then?
My grant is due tomorrow. I just need to know if I can just use 3 patients per group.
Okay, well, you probably should have come to me earlier for help with this.
All I need you to do is tell me that 3 patients are okay.
So, it is not that easy. Your marker for apoptosis may have a large amount of variability associated with it that could make it difficult to ascertain differences based only on 3 patients per group. It also depends on what kind of outcomes you are looking at. Are you looking at normalized changes in expression levels from baseline? 3 patients may not be sufficient to detect differences in these expression levels between the different treatment groups.
I do not understand.
I'm saying that you may need more than 3 patients per group, but that I need more information to determine that.
The serine protease granzyme B is made in cytotoxic lymphocytes, where it is inactive due to the low pH of the storage granules. It is measured immediately upon delivery into target cell cytoplasms, where the pH is neutral. This is followed by cleavage of procaspase 3 by granzyme B in the target cell cytoplasm and the subsequent induction of apoptosis. All proteolytic events can be quantitated at the live single-cell level by flow cytometry and imaged by confocal microscopy.
I understand very little of what you just said. Maybe we should talk more about this.
I just need to know if 3 patients are enough. My grant is due tomorrow.
We will need to meet to better understand this before we can determine the appropriate sample size.
I can put you on my grant for 0.5% FTE. You can design and analyze the data later.
Do you really think that is enough to do the work?
Well, it may be less if it is awarded and the budget is cut.
Please go away.
Okay, good. All right, so there's lots of deep messages in that, and there's another one. There's a whole series, I said, Publish or Perish, and the p-value, and so on. You can find them, I'm sure. Okay, that's worth looking again, because there's actually some quite deep